Let's jump right into this explainer. Imagine a technological breakthrough that could literally change how we detect one of the most elusive medical mysteries of our time. We're looking at a completely revolutionary approach to medical imaging today, one that doesn't just look for a tumor, but actually hunts for the invisible footprint that a tumor leaves behind, sometimes years before it even forms. So if you've ever wondered how advanced computational math could transform a standard everyday hospital scan into a life-saving early warning system, well, you're in exactly the right place.
To really grasp the stakes of what we're discussing, we have to talk about a pretty dismal number, 12%. That is the current 5-year survival rate for pancreatic ductal adenocarcinoma, or PDAC. It's a silent killer. And the reason that survival rate is just so tragically low is that this disease typically presents absolutely zero symptoms. It produces no visible mass on a standard scan until it's locally advanced or is already spread. I mean, over 80% of patients are diagnosed far, far too late.
But beneath that grim statistic lies a hidden biological timeline. And here is the crazy part. The biological window for detection is actually estimated to be 10 to 15 years. This disease doesn't just pop up overnight. It develops through a really well-characterized progression known as pan-IN. It systematically remodels the tissue environment, causing fatty infiltration, inflammation, cellular changes for over a decade before a visible mass ever actually appears to a radiologist's naked eye. The clues are absolutely there. They've just been invisible to our standard way of looking.
Now, recently, artificial intelligence has stepped in to hunt for these invisible clues. But there's a catch. Current deep learning models can flag cancer with really high accuracy, but they operate as these totally opaque black boxes. They might tell a doctor, hey, there's cancer here, but they can't explain why in actual biological terms. Enter a new method called Virtual Spectral Decomposition, or VSD for short. VSD offers what we'd call a transparent glass box. It provides computational histology. Basically, that means every single mathematical feature it finds can be directly traced back to a specific, named biological tissue.
So the absolutely crucial point here is how VSD actually achieves this transparency. It isn't just some machine learning algorithm searching for mysterious pixel patterns. Instead, it relies on established radiology physics. Standard CT scans measure tissue density in something called Hounsfield units. VSD applies specific mathematical functions, parametrized sigmoid curves, to decompose that density access. It literally maps your standard, run-of-the-mill grayscale pixels to actual, named biological tissues based on their known physical properties. Think of it like a prism. Just as optical spectroscopy acts like a prism that splits white light into specific, measurable colors, VSD uses these 6 distinct curves to isolate specific biological colors. It takes all that flat black and white data from a standard CT scan and essentially splits it out. This allows the computer to independently measure things like fat, fluid, and stroma as totally separate, distinct layers of information. By feeding a scan through these mathematical curves, this system creates 6 distinct biological channels: fat, fluid, parenchyma, which by the way is just the functional tissue of the organ, stroma, vascular, and calcification. Because it isolates these specific tissues, VSD can actually measure the physical collapse of healthy pancreatic architecture and track the abnormal growth of tumor-supporting structures. It's essentially performing a digital biopsy using nothing but a standard CT scan. How wild is that? This leads to what researchers are calling the lone fire signature. By using a morphological technique to find isolated structural pixels, basically pixels that are firing all alone without their normal neighboring tissue, they found a very distinct fingerprint of cancer. In healthy pancreas tissue, the structure is totally dominated by fat. But as a tumor takes hold, that healthy fat completely collapses, and isolated vascular and stroma structures start to wildly surge. The end result of that collapse is really striking. By the time we look at the actual malignant tissue, the healthy, organized fat architecture is virtually gone. It makes up less than 2% of the isolated structures. Instead, it's been overwhelmingly replaced by a chaotic, disorganized mix of surviving vascular tissue at 45% and dense desmoplastic stroma at 32%. So this isn't just a minor change in density. We're talking about a total architectural takeover by the cancer. And by analyzing hundreds of patients, researchers were able to map out this highly logical 4-stage biological collapse. It starts off quietly with subtle composition shifts in fat and fluid. That triggers the actual physical remodeling and destruction of the fat architecture. From there, the disease progresses into a major shift in firing patterns as that desmoplastic stroma forms.
ultimately ending in total global reorganization and a complete vascular takeover of the tissue. What's so important about this progression is that it proves these changes aren't just random computer noise. The data tracks perfectly. It goes from healthy tissue straight through mild and severe field effects and culminates in the tumor itself. It follows the known biology of tumor development exactly, which gives us explainable structural clues at every single step of the disease's evolution. Now, we all know that in medical research, a tool is really only as good as its ability to work in the real world, right? To prove this wasn't just some localized fluke, the researchers validated their exact same mathematical parameters without doing any retraining across 3 totally independent datasets. Whether they were looking at NIH reference data, the MSD dataset, or the multi-institutional CPTAC dataset, VSD maintained incredible accuracy. It hit an AUC of up to 0.961 for detecting cancer-bearing pancreases, and that's across totally heterogeneous, everyday hospital scanners. But perhaps the most staggering finding of all is an exploratory case of a single patient. They're labeled C3N01375. This patient had a CT scan 1,394 days, that is roughly 3.8 years before their actual pathological diagnosis of pancreatic cancer. And yet, their VSD severity score was already 2.8 standard deviations above the healthy mean. Think about that. The tissue transformation was already loudly signaling on a scan almost 4 years early. Which leads us to a pretty profound realization. The researchers noticed that the signal was actually stable across time, meaning it didn't just slowly get worse day by day, leading right up to the diagnosis. This suggests we aren't just catching a fast-moving tumor a few months early. Instead, VSD is potentially identifying an entirely new, stable precancerous tissue state that just exists in the body for years before the invasive carcinoma actually forms. However, to maintain rigorous scientific integrity here, we definitely have to emphasize some crucial caveats. The data we're looking at is entirely retrospective. And more importantly, most of the scans in that timeline analysis were staging CTs. That means doctors already suspected a problem when the scan was taken. Even that incredible 3.8-year case we just talked about is a single exploratory data point without its full clinical context. So to truly prove this works for early screening, prospective trials on truly incidental, everyday CT scans, the ones taken for completely unrelated reasons, are the absolute critical next step. All of this leaves us with an incredible, genuinely life-saving possibility to ponder. We now know the biological window is long, and we finally have a transparent mathematical tool that can read the hidden tissue signatures of that window. So if our standard hospital imaging is already capturing these invisible clues, could your next routine scan run through the right computational prism, stop a silent killer years before it even starts? It's a deeply fascinating frontier for medical technology, and it's absolutely one we'll be keeping a close eye on.